In this video, we're going to talk about solving inequalities. Now, before we get started into solving anything, here is just a quick recap of what each inequality means, what it would sound like in a sentence, and finally how it would look like in a graph. I would definitely write these down just so you have something in your notes to come back to when we're solving more complicated problems that deal with inequalities. Now, one of the most important things that you want to remember from Algebra 1 when moving forward with this is that when you multiply or divide by a negative number when solving an inequality, that sign will flip. So you'll see that in the next problem that we do. Problem number 2 asks, what is the solution of negative 3 times 2x minus 5 plus 1 greater than or equal to 4, and then graph the solution. So first we'll start out like normal by just solving for x. So we'll carry out that 3, or negative 3. Then I'm going to want to combine everything on the left side together. Finally, I want to bring that 16 over to the other side to bring it with the 4. And I'm left with negative 6x is greater than or equal to negative 12. So now, my last step to get x by itself will be to divide by negative 6. When I do that, keep in mind, since I'm dividing by a negative number, this inequality is about to flip. So I'm going to finally be left with x is now less than or equal to positive 2. And if you want to double check to see if that's correct, plug 2 or 1 or any number less than 2 into this original equation and see if it holds up. Now finally, the last part of this is graphing. On your next test or any quiz that you see dealing with this, I'll give you a blank number line, and then I would suggest just kind of labeling a couple checks around like the number that you want to graph. So I'd probably just do something like this, since I want to just graph the dot 2. So now I'll go to 2, I'll put a circle around it. I'm going to cover it in because it's less than or equal to. And then I'll mark an arrow going to anything less than 2. In this next problem, they're asking, is the inequality always, sometimes, or never true? So this is going to tie into what we did last section in 1.4. So let's solve through this inequality and see what we find out. We'll carry out the negative 2. Now I see here on both sides I have a negative 6x, so I can just cancel those out. And now I'm left with the statement negative 2 is greater than 7. Now the value of negative 2 will never be higher than positive 7, so this is going to be an example of an inequality that is never true. So kind of recapping what we said about these equations yesterday, you can try to plug in any value for x into this original equation, and this inequality won't hold up. In the next example, let's again solve for x and see what kind of statement we find. We'll get rid of those parentheses first by carrying over that 5. Now finally, I'm going to combine the 10x and 7x on the same side. Now again, I have the same 3x and 3x on both sides that I can cancel out. And I'm left with the statement, negative 15 is less than or equal to 8. Now on the other end, comparing back to part A, this statement will always hold true. The value of negative 15 will always be less than 8. So this is an example of an inequality that would always be true. The last thing that we're going to talk about today is compound inequalities. Compound inequalities combine two inequalities with the statement and or. So we're going to look at an example of both and see what they look like on a graph. Our first example is solving with an and inequality. What is the solution of 7 is less than 2x plus 1 and 3x is less than or equal to 18, and then we want to graph it. So for this series of equations, I want to find a value or values for x that'll satisfy this equation and the other one. So to start, let me just solve for x. I'll subtract the 1, divide both sides by 2. I'm left with 3 is less than x. I usually just kind of like to flip it at this point and have the x on the left side, so I'm always kind of reading them the same way. Now on the other end, all I gotta do here is divide by 3. And I have x is less than or equal to 6. So I'm left with these two inequalities. I can have any value of x that's greater than positive 3 and less than or equal to 6. So what I'm going to do here, I'll start by graphing 3. I'm not going to fill it in because it's just greater than. I'll shade up until I get to positive 6. I will shade that in. And then I'm done. So also just to recap, to double check this, if you want to plug in 4, 5 to either of these equations, you'll see that they'll both hold true. Any value in this kind of segmented area over here will work if you use that value for x. Whenever you have an and inequality for the compound inequality, it'll look like a line segment pretty much. The last problem that we're going to look at is an or inequality. What is the solution if 7 plus k is greater than or equal to 6, or 8 plus k is less than 3? And then we want to graph it again. So in this equation, it either has to satisfy this or this. So to start, again, I'll just solve for k. -1. And over here, so I'm left with these two inequalities. K could be greater than or equal to -1, or k could be less than -5. So to graph these, I'll go to -5. I could be less than -5, so I'll go this way. And then for the other one, I'll shade it in because it's greater than or equal to. And I'll go this way. So it's important to note here is that when you're doing an or compound inequality, the graph will just look like two opposite rays going in opposite directions.